So if you have a differential equation and you want to find a particular solution, well, this is very similar to questions we've already done. The only thing difference is we're talking about differential equation instead of like if you have the derivative and want to find the antiderivative, we've done that by solving for C in the past. You need a specific point to plug in to solve for C. Well, this is exactly the same idea. Here is our derivative. If I want to find a particular solution, this is like asking us to find y. So we've done this question before, just the wording has changed because now in a differential equation they say find a particular solution. So I could find my integral, which use my integral rules. E to the 2x would stay the same, but it has a chain rule, so we have to divide by 2. The negative 2x squared, we add 1 to the exponent and divide by 3. And of course, we have plus c.
Excuse me, interruption, staff and students. At this time, can I have the championship soccer indoor team to the cafeteria?
So then because we have an initial condition, you know that when x is 0, that y is 4, we could solve for c. So we have an initial condition right here. And now that I've got my integral, I can plug in 0 for x, 4 for y. The only thing I don't know is c. A little bit of rearranging, and we get the value of c. So now our particular solution is there. Oh, something from yesterday's or the last two examples we did, they were both equal to 0 here. They should be, you can change them. This should have been in both the examples yesterday. This should have just been y. So if you want to go back, that makes a little bit more sense that those were both y. Question? So again, we have different questions that are worded just a little bit differently. We have to still pull out what is the differential equation, what can we pull out from here. So a curve has a slope, and this idea of slope here, that's your derivative, right? Your derivative finds slopes of tangents and says the slope is this at every point. That's telling us that's our derivative. What is the equation for the curve? That means it wants us to find y if it passes through this specific point. So we're going to have to find our integral. And the integral of cos, well, that'll be sine, but since there's a 4x, we would have to divide by 4. So you see how that 8 changed to a 2. Because if you did the integral of cos 4x, well, there would normally be a regular chain rule which multiplies by 4. Since we're integrating, we have to compensate for that. So we divide by 4, so your 8 changes to a 2. And now we have our initial condition here. We know that when x is pi over 8, y is negative 2. So now we can solve for c. That is one ugly looking 4. and we get our original equation. So it's kind of nice that these first couple questions, they're completely review. We've done solving for C before. Nothing is really new at this point. This isn't new either, it's just a little bit harder. So now let's problem solve a little bit. Okay? So again, in this unit, if we have a differential equation and we want something to be a solution, we need to work backwards to find out if that would be the original equation. So if my second derivative was 25, second derivative plus 25y happens to equal negative 82e to the negative 4x, could this be a solution? And if it is, what's the value of k? So we're going to start with that y, and I could easily find the derivative of y prime. And I could easily find the second derivative, y double prime, in terms of k. Now my differential equation has a y double prime, and it has a y, and it's equal to negative 82e to the negative 4x. So where the y double prime is, I could substitute, and I'll put it in blue brackets here, right? All I did was substitute in the y double prime for that part. And I'm going to change these brackets to green. Because all I did where the y was is substitute in my original y value. And I need this to be a solution. In other words, I need my left side to equal the right side to be a solution. The only thing I need to have work out then is to figure out what k is. Something nice happens with our signs. Right? They were initially scary in the equation, but they cancel out beautifully. I have some like terms on the left-hand side. 16 plus 25 is 41. And from here, it is not hard to get k by itself. You can divide both sides by the e to the negative 4x. 41k equals negative 82. And k would just equal negative 2. So a differential equation can have multiple rates of change in it, and the original equation in it. So this y double prime plus 25y, these are very much like our implicit equations that we've done in the past. So now, when you're working with a particular solution to this, in the blue, we figured out if that was my particular solution, it has a y prime, it has a y double prime. Does it work for this differential equation, which has a y and the y double prime? We could plug it in, check things out, and in this case, we could solve for k. So just like when we found the antiderivative, we had a plus c because there could be any c at the end or any c available. Sometimes in differential equations, we have a general solution where something represents every single possible form of the solution, and we have a c value as well. So here, we want to verify that this equation with a constant c is the general solution to that differential equation. So to start with, we could take the derivative, implicit differentiation, of both sides of our original equation. If we do that, we can see if we can get dy dx by itself. So remember implicit differentiation. You're going to take the derivative with respect to this, with respect to x of everything. And when you have x cubed times y, you're going to have a product rule. And whenever you have a y, you have a chain rule, so you always have to write dy dx afterwards. The derivative of x squared equals 2x. Then we subtract. And notice that I put brackets. Ooh, I'm going to make my brackets bigger and square and fancy. If you're subtracting a product rule, make sure you put it in brackets. Or, if you screw up so much with subtracting, which is a very common thing, and you have a product rule that's subtracted, you can always, like, this is not a bad strategy, so you don't screw up. Why not just rearrange your equation so it all has plus signs? I can move that, like, I am prone to screw up with negatives. So why don't I make my life easier by avoiding that negative? Then I don't have to worry about that big set of brackets and distributing the negative. This little step of moving that x cubed y to the right-hand side earlier saves you a whole bunch of hassle. You don't have to worry about distributing it in negative later. It'll just happen naturally. It might make your life easier. However, we are also creatures of habit, and if you see implicit differentiation, you probably just jump right into it without thinking about the negative. Then you have to deal with that. So either way is fine. Wherever we have the y, we have a dy dx. So we have a dy dx here and a dy dx here. Our job is going to be to try to get that by itself using algebra. So we move things, distribute that negative, move things around, get all of our dy dx's on the left side, move all of our terms without dy dx's to the right side. And we can divide. Make a little happy face. It looks exactly like we want it to. Yay! And this is a general solution because it doesn't matter what c is, this differential equation will be the same. Because when you do the derivative implicit differentiation of a constant there, it's going to go away and be 0. So that number by itself didn't matter. So we have a second order, degree 1 differential equation. Do you remember how the order and the degree worked? Second order because it's the second derivative. Degree 1 because we only have that second derivative once with an exponent of 1. I can get the d2y dx squared by itself. And if I take the integral of that, I will find the antiderivative, which will need a plus c. And since we're going to have more than one c here, this time I wrote it as a c with a little 1. You could use different letters. You could just say plus C, and in the next line go plus D. That would be fine as well. So this would be my derivative equation. And if I wanted to find the general solution back to the original, now I'd have to integrate that again. And I'll get a C1x, and now I'll have a plus C2. So C1 and C2 both can be any real number. C1 belongs to all real numbers. C2 belongs to all real numbers. We're almost done this unit.
Okay, let's stop.
Isn't that crazy? Our last unit had 2 booklets of 50. This is the full unit. This isn't like we broke it up into little drinks.
I think we should stop.
We should stop.
Stop and we have discussions. Stop and let's do book really quick.
But we're behind the other class.
Oh yeah, let's start it off. Yeah. Don't we have like a guidance? We don't understand what we're at.
How'd you do?
We just stood there.
Stood there? Like champions?
Actually, this is the thing that people do. People like stick this on paper. It would if you peel off the. It would if you peel off the.
Okay. Oh my goodness. Going back on the video here.
I hope nothing's unmuted.
Okay,
Put the phone up to
there we go.
I'll put it for the video back then, Mitch.
All right.
Good video.
So if we want to find a general solution to something, we have to work our way backwards. So we're going to integrate to find our antiderivative. And of course you have a plus C. So is this really new? Not really. We've been doing this all the way along. But now it's called a general solution to a differential equation instead of just can you find the indefinite integral or can you find the antiderivative. And then instead of just solving for C, now we have this language of can you find a particular solution? So what do? We plug in 0 for x and solve for C. Once you solve for C, you write down the particular solution. So find the equation of the curve passing through 1, -1. And the slope at any point is this. So telling us the slope at any point, what does that tell us? That tells us a derivative. And if we know the derivative, we can integrate to find the particular solution. And of course, you'll get a plus C, which now that you know you have a specific point, you can plug that in and solve for C. And get x cubed minus 2 as the equation. So most of what we've done today has been review of stuff we've done before, which is kind of nice. Because you guys have learned a ton already in calculus. So we can have differential equations, of course, in kinematics as well. Right? We want to find S. Think of sva. We have the velocity, so if I want to go back and find S, I'm going to have to integrate. And that's a beautiful little integral. T to the 4 plus c. We know that when t is 0, S is 4. That tells us that c is 4. And so we get S of t is t to the 4 plus 4.